It's now my pleasure to introduce today's speaker, Professor Emmanuel Gull from University of Michigan and University of Warsaw. So, yeah, Professor Gull is an expert on condensed matter physics, especially theoretic methods and analytical methods to study many-body electronic systems. He studied, he's originally Swiss, studied at ETH, then did PhD in Columbia University, had research posts in other places like Dresden, then was full professor at University of Michigan, and recently he was awarded a very prestigious grant, ERC Advanced Grant, to come to Poland, to University of Warsaw. And there are very few such prestigious grants awarded to Polish universities, so we are very happy that you joined Polish scientific community. Yeah, and without further ado, I give the floor to you, Emmanuel.
All right, thank you very much. Yeah, let me get started. So this is a colloquium talk. It will be very general. It will have very few details, but please, by all means, interrupt and ask questions whenever you're interested. Most of the work that I'll present today has been done over many years by a range of graduate students and actually an undergraduate student, Gianni here. Lei and Yang are still my two graduate students in Michigan. Jianan has moved on to the Flatiron Institute in New York, and Andre just got a faculty position at the University of Georgia. It's also, a lot of it is done in very close collaboration with Dominika Skid, who is also at the University of Michigan and now the University of Warsaw. But let's take a step back. So I heard that you're doing, astrophysics and quantum information in this colloquium. And so it's always good to remember what we're actually doing in physics, right? We are trying to understand nature, and we are probing nature by conducting experiment and then trying to explain nature by constructing appropriate theories. And even back in like 965 here, al-Basri, a Islamic philosopher, said that if we are to make progress in this endeavor, we really ought to check our theories with experimentation. And we've done this on and on. Newton's law, for example, is something that we know in daily life, and clearly we are very familiar with experiments like falling down, and Newton from that constructed a theory that has been very, very successful. Every now and then it works the other way around. Here we have Albert Einstein with the general theory of relativity, postulated more or less on mathematical principles. And next to him, Mr. Eddington, who back in 1919 took a boat to the southern hemisphere to observe the passing of planets behind the Earth here to check, to validate that theory of general relativity. And in this way, it goes back and forth with theory ever surpassing experiment and experiment, validating theory and the other way around. And perhaps the best example of how this works in practice is quantum electrodynamics, which for the purposes of this talk is characterized by a single, number, the fine structure constant here of alpha, which is E squared over H bar C. So it characterizes the relationship between the elementary charge, the Planck constant, and the speed of light. Now, the same Mr. Eddington that took his boat over to the southern hemisphere back in the 1930s, the late 1930s, had a theory about the number of particles, in particular charged particles in the universe, and therefore proved mathematically that alpha had to be exactly 1 over 136. Well, it was the 1930s. Experiments were done on the fine structure constant. They became gradually ever and ever better. And, shortly after, it turned out that it was actually more like 1 over 137 than 1 over 136. Mr. Eddington, being a proper physicist, went back over his theory, tried to find out where the mistake was in his counting arguments of the number of charged particles in the universe, and figured out there was a small mathematical correction that had to be applied that really, turned out that alpha was exactly 1 over 137. The 1940s happened with that, a short break in that type of experimentation. And after the war, the experiments, became much, much more precise. And it pretty soon became obvious that alpha really was not 1 over some integer number, but, something like 1 over 137.0359979 and so on. And experiments became more and more precise, and nowadays we're at a place where both direct measurements of the fine structure constant and a combination of quantum electrodynamics calculations and the measurement of the magnetic dipole, validate that theory to a ridiculous amount, to a ridiculous precision. And of course, we have various Nobel Prizes, including these here, awarded for that type of theory. Now, I myself, I'm a condensed matter physicist. And if you think about the fundamental laws of nature that make up condensed matter, well, it's not gravity, it's not the strong force, it's also not the weak force. It really is that theory that makes materials like this hold together. And so you can, now that we've understood quantum electrodynamics, you can take it and just basically say, well, the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known. And really the only difficulty is that the exact application of these laws leads to equations much too complicated to be solved. In principle, this could be a research program, right? We all solve the hydrogen atom, somewhere in undergrad. Let's take it, let's ramp up the nuclear charge a little bit until we have the elements that we care about, say iron, nickel, plutonium, right? Let's take those atoms, put them into one-dimensional chains, take the chains, put them into two-dimensional planes, take the two-dimensional planes, stack them on top of each other, get three-dimensional crystals, and we should get, the behavior of this chunk of material over here right from the application of that theory. But that, as already Paul Dirac said in 1929, is not a practical way forward. And it therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed, which can lead to an explanation of the main features of complex atomic systems. And he finishes this sentence back in 1929 with "without too much computation." Now, is it really that simple? Well, as Paul Dirac already told you, we've understood physics here, right? Quantum electrodynamics really solves problem. Chemistry is just an application of that, right? In fact, molecular biology is just an application of chemistry. Cell biology is just an application of molecular biology. And you can go down that hierarchy until you end up with psychology and the social sciences, which are just, applied psychology. But at the latest, at that point, if you are trying to explain the sociology of Donald Trump with a microscopic Hamiltonian, you see that you're missing a step somewhere in between. So as you went down that hierarchy, something else happened. Somehow taking these particles and adding them together and stacking them up and doing more with them is really something different from just solving a microscopic Hamiltonian more and more precisely. And that is something that P.W. Anderson back in 1972 sort of wrote down in a very sort of groundbreaking paper where he defined the phenomenon of emergence as we go down those length scales and as new and more complicated and more interesting aspects of physics emerge. Right. Now, emergence doesn't happen just at the large scales. It is a phenomenon that we find all over physics and all over condensed matter. Superconductivity, where many electrons conspire to bunch up to build currents without resistance, where you can have magnets levitating on top of a superconductor. It's a typical example of emergence. Magnetism, where lots of magnetic particles or electrons conspire to arrange themselves in magnetic patterns. You see here a chromoscopy picture of a typical magnet, right? That's a typical sort of phenomenon of emergence. The Kondo effect, right, where we have in this case a surface of copper and a cobalt atom adsorbed on it, and this is imaged with a scanning tunneling microscope here, showing you that there's a large charge density on that cobalt atom. That is a typical phenomenon of emergence where many of these electrons bunch up on a single sort of spatially resolved point over here. Quantum criticality, charge order here, a typical other phenomenon that you find all over sort of strongly correlated electron materials. But you don't have to go to condensed matter to find these phenomena. Here I have an example of a quark-gluon plasma that is formed at the collision point of two relativistically accelerated gold ions from the relativistic ion collider at Brookhaven National Lab. And that too, of course, is an emergent phenomenon. So why do we care, right? What is it that those emergent phenomena give us? Well, you can look at oxide electronics, for example, and the correlated materials that are used in oxide electronics. You can look at high temperature and high magnetic field superconductors, and you can also look at catalysis. Now, oxide electronics and correlated materials inside of batteries and solar cells really give us our new generation of self-driving cars and rooftop solar cell arrays. If we're thinking of beating Moore's law, so of building transistors that are ever dense, have ever more charge densities, or ever faster, right? Oxide electronics, where the charge densities are massive in compared to typical semiconductor electronics, would be a way out. Now, if any one of you ever had to have, anything from a hip replacement to a broken bone or a suspicion of that somewhere else, you might have been shoved into a magnetic resonance imaging domain, right? What we have in there are both superconducting magnets in here and very, very strong magnetic fields that we're getting. One of the reasons the helium prices are so ridiculous right now. If you're living in a dense urban area, for example, if you're living in Manhattan, Manhattan is an island. It's connected to the power plants on Long Island with power cables. Those power cables can't just go through the neighborhood. We actually bury them on the ground. We build high power density superconducting cables that carry the power from the power plants into the dense urban areas where we actually use that power to, power Wall Street. That's a typical emergent phenomena, an application of high magnetic field superconductivity. And finally, if you just think of fertilizer production or the efficient way of taking molecules, performing chemical reactions, and then getting rid of those molecules from the surfaces here where they have performed these reactions, that catalysis process, that's a typical strong correlation phase transition where we take something from far apart, we bring it onto a surface. In physics, we would change the interaction parameter U. In chemistry, we change the distance, the hopping T, right? Go from weakly correlated to strongly correlated to weakly correlated in such a way that we use about, I think it is 5% of humanity's energy for fertilizer production, and at the same time, keep about 2/3 of humanity alive. All right, so that's the theory problem. How do we solve it? Well, it's not as easy as just stacking a bunch of atoms. Typically, if you look at a chunk of material, 10 to the 23 number of particles is a good sort of number that we have. And typically for the regimes that we're interested in, there are really no small parameters that allow us to do perturbation expansions. At the same time, we need a ridiculous precision to understand these materials. We're starting somewhere on the Bayer scale with, about a heart rate. Now, if you take a heart rate, that's about 27 eV. 1 eV is about 10,000 Kelvin. You do the math, you see that the Bayer energy scale of your atomic excitations is somewhere near 300,000 Kelvin. If you look at any one of those compounds, you find that the phase transitions happen, somewhere near room temperature. That's why we know about them, right? Give or take an order of magnitude. And if you're looking at correlated materials and you want to know on which scale you get either one phase or the other phase, so you're looking at competing phenomena, then you're talking about energy differences of 3K. So you want to do a calculation, you better be specific to that type of energy range. In addition to that, what we care about is not just the ground state energy or the electronic structure of a material. If you ever talk to an experimentalist, you see that what they are measuring here is angle resolved photoemission spectroscopy, scanning tunneling microscopy. This here is STM here. Neutron spectroscopy, nuclear magnetic resonance, resonant inelastic X-ray scattering, Raman scattering. All of these things have nothing to do with ground state energies. They are all about excitations. They measure the perturbation of a system exposed to typically a weak external probe. And so just knowing the ground state is not good enough. You got to be able to say something about experimental response function as you measure them here. Typically, as we are studying these materials, we don't just have one phenomenon that might possibly occur. And the actinide series here is a very good example of this. What you see over here is temperature. This is in room temperature and it's too small. I apologize for that. Going from somewhere near 0 Kelvin to somewhere near 2000 Kelvin for actinium, thorium, palladium, whatever, uranium, and all of these, here is plutonium, all of these different materials here. And you can see that if you, for example, take plutonium at ambient pressure, and you start heating it up, starting from 0 Kelvin, you go through 6 different phase transitions of various phases of plutonium, all the way up until you melt it into a liquid. Why does that happen, right? It's clearly a finite temperature. It's a statistical mechanics phenomenon that is happening over here, right? And we ought to be able to explain this, but in order to explain this, we got to know about temperature, we have to know about entropies, and we have to know about excitations so that we can probe these things. So historically, if we're trying to understand these things, there are really 2 types of approaches. One is that we just basically say, we know the theory, that's quantum electrodynamics. We're going to take the theory, well, let's throw out relativistics, let's go to a non-relativistic sort of Hamiltonian formulation, and let me approximate the solution with, for example, mean field theory. This business mean field theory is called Hartree-Fock. Density functional theory is a typical approach like that. You try to take the entire system, solve it in some approximation in practice, right, and you get something that you then would like to compare to experiment. Alternatively, we can do, so this is the approach that most of material science and a lot of quantum chemistry is taking for understanding molecular and solid systems. Alternatively, we can say that, well, really that theory, the entire electronic structure is way too complicated to understand. So what we got to do is we got to find the relative degrees of freedom that are relevant in this particular problem, and we got to go find an effective low energy theory. And once we have this effective low energy theory with a couple of free parameters, we can screw around with those parameters and get an approximate solution to this approximate construction that we can then compare to experiment. And of course, it's fantastic when it works, but those cases that are interested are the ones where neither one of those approaches really gives you the right result. And the question then is, what could you possibly do? Back to what Paul Dirac said in 1929, it says, approximate methods of applying quantum mechanics should be developed, which can lead to an explanation of the main features of complex atomic systems without too much computation. And so really that's sort of what my research field is about, right? How can we take this type of research program and these types of systems that I've shown you and get to solutions that we can bring to the experimentalists to try and understand what's actually happening in the lab? So I work on investigating strongly correlated electron systems using modern computational methods on computers that are, somewhat larger than your cell phone and amongst the largest in the world. It is exactly Paul Dirac's program. The only compromise that I've made is that about 100 years later, without too much computation, really has a very different meaning from what it used to mean back in 1928. So let's take a step back, right? What can we actually do when we're talking about calculating materials? And, it's important to say that in this business, there is a theory that works extremely well for a lot of materials that we care about. It's called density functional theory. It is a theory that works purely on electronic densities of materials. It's in principle an exact theory. Of course, in a computer, it has approximations, and those approximations are often uncontrolled, in a sense that there's no systematic improvement to make this theory more and more precise. It works really well for ground state lattice structures, works really well for phonons, works really well for solid with light elements. Anything to do with biology and most of chemistry is in here, right? And it is what gives you Fermi surfaces, band structures, or at least the occupied band structure of simple solids. Almost as importantly as that, it is now at the place where I can take an undergraduate student of one of my experimental colleagues, tell him to go download a package and run it for the material of interest of that person. And very often what comes out is not completely crazy. And so really those two things have led to a Nobel Prize in Chemistry back in 1998 for Walter Kohn and John Popel for the development of density functional theory and the development of computational methods in quantum chemistry. Now, that's great. And really it's important to emphasize that a lot of stuff works really nicely. But very often the stuff that works nicely is not the stuff that we need in condensed matter physics. In physics, we would like to really connect what is happening in experiment with what is happening in theory. Often the systems that we care about, all the systems that I showed you previously, are systems where we have strong electronic correlations of either d or f electrons. very often the phenomena that we care about are phenomena that are observed at finite temperature. So temperature ought to be a part of our theory. When we are observing things, we're doing this in typically an optics experiment or a neutron experiment or some other experiment where we take our chunk of material and then we whack it with a probe and we see how it reacts, right? That's, you know, response theory of some sort. So that's not a ground state question. That's a question about excitation. Often we're observing transport, we're observing time dependence, you know, we're observing phase transition. And so there's a lot of non-equilibrium in all of this. And at the same time, even as numerical physicists, we would like to talk to our theory friends who often develop very simple, you know, theories that have theoretical insight that we then, you know, either can validate or disprove with a more involved calculation. That's the physics perspective. There's also an applied math perspective that I myself like very much, which is that if we give you a result, we ought to be able to give you a confidence interval error bar or some other, you know, idea of whether you should believe us or not. You know, in numerical mathematics, if you do it right, you get a priori and a posteriori error estimates. Of course, in science, we're often very far from that. We would like to have a possibility for refinement. So we may be able to give you a shitty result and tell you that it's not really good, and tell you that if you give us 10 times more computer power, we're going to get you a better result, right? And so once that grant gets proved, we'll come back to you with a result that is one order better, or, you know, is a chemical accuracy or whatever. We'd like to have uncertainty estimates, and most importantly, we'd like to take free parameters out of the theories, because we want to have something that ab initio characterizes nature and doesn't allow us to have tuning parameters that possibly would lead us to, you know, put in the physics that we would like to get out. And so, you know, theoretically, we have a framework to do that, right? Consider an electron, and it somehow is on its merry way through a solid, and every now and then it bounces into another electron or a nucleus, and we know precisely what that theory is. In fact, we understand it to some ridiculous precision. That's just quantum electrodynamics. And so basically we can take this and we can look at processes where I have an electron and then it bounces into another one, which bounces into another one, and so on. And if we take all of these processes and we add them up with the right probability distributions, we're pretty much getting the exact result. And that is straightforward to do on low order on paper. It is just a diagrammatic quantum field theory of the 1960s. But of course, it's not going to be valid for those very heavily correlated electrons, where very many of these processes matter and all of it at the same time. But much of the formalism that was developed in the 1960s on a piece of paper for these types of diagrammatics, for these types of processes, much of that formalism remains relevant. Basically, all we need to do is apply it to realistic solid. Now you ask, you know, why the heck has nobody ever done that? And, you know, it helps you to just basically sit down with a piece of paper and look at what's actually involved for doing second order perturbation theory or random phase approximation for an actual realistic solid, right? Let's take the finite temperature formalism. I talked to you about, you know, the need to resolve both the bare energy scales and the temperature at which the physical phenomena happen. If you do the math, you see that there are billions of frequencies that one needs to resolve just to get the temperature to energy resolution that one has in these compounds. If we look at the Coulomb scattering tensor, where one electron comes and another electron, they bounce into each other and then they go away again, right? That is for an incoming state and an outgoing state for each electron. That's a rank 4 tensor. It looks something like that if we put it into a basis. You know, at the very least, you need about 120 orbitals per unit cell. You want to have a couple of momentum points so that you can do the momentum resolution. If we say 4 by 4 by 4, any sort of electronic structure theory person would laugh us out of the room because it's way too little. But if you say 120 orbitals and 4 by 4 by 4, that would already use about 405 terabytes of storage. That thing has 1 terabyte of storage. We can do 405 terabytes of storage. I mean, it's tedious, but it would be doable to look at objects of that size. Now, writing down that object is 405 terabytes of storage. Every one of those diagrams, every time one of those electrons bounces into another one, we're going to have to do a calculation where the main ingredient of the calculation is 405 terabytes of storage. And so you're starting to see that you're getting into a real applied mathematics problem. Like, how can you do that, and how can you do this efficiently? And basically, that is the reason why even the standard, simple finite temperature field theories have not really been explored until very, very recently. And it is really the 14-year-old gamers that came to help us in that respect. If we look at Feynman diagrams, up here I have one. I have two of these wiggly lines. Those are two of those 405 terabyte lines. I have, three of those solid lines. Those are electrons that are propagating. If we look at a diagram like that, that's a second-order self-energy diagram. Details here really don't matter. It is basically a glorified matrix contraction or a tensor contraction. It consists of having to do lots of matrix multiplications for a lot of data. Traditionally, we would do that on a CPU. If we are very efficient on a single core, we can get about 20 or so gigaflops per core. If we take a high-end CPU, we have about 128 cores or so. We can probably get to about 1 teraflop per second. What is 2 plus 2? 4. What is 2 times 3? What is 8 plus 8? You can see that as standard physicists will get you about, 1 floating point operation per second, right? A kiloflop would be 1,000. A megaflop would be 1,000,000. A gigaflop would be 1,000,000,000. It was even integers, but I allow for round-off errors up here, right? We're theorists after all. So you can see that by the time you're doing a teraflop, this is an insane mathematical power of just sheer muscle of doing multiplications. Now, this is on a typical high-end CPU. In your computer, you typically also have a graphics card. And even a couple of years back, this is 2017 GPU, we have about 7.8 teraflops per second per GPU, and typically about 6 GPUs per node. Nowadays, we're at about 100 teraflops per second. Each one of those cards sets you back about $10,000 US. And again, you can fit about 8 of those cards into a typical node. You can fit about 40 nodes into a rack. You can fit about, 5 by 10 racks into a computer center, right? And then you see that now we have the strength to do the diagrammatic theories of the 1960s. And so here's this, how this is done. What you see here is the number of GPUs. This only goes to about 120 GPUs. This is the speed up. Dashed is ideal. Red is practically achieved. What you see here is the arithmetic, the teraflop numbers per node. You see that we're somewhere near 70% of peak efficiency, which is basically unheard of, these types of calculations. And you can see that as a consequence, if we run this on large enough computers, we can get the time to execution really down, which allows us to, in practice, do calculations like that. Over here, you see a typical calculation of a specific heat and entropy and an energy. And the fact that there are multiple curves that are right on top of each other just tells you that self-consistent many-body theory actually works in practice for real materials, for real systems, and we now have the muscle to do that. That back, a couple of years ago, took a calculation at the largest computer of the world. Nowadays, we are getting more and more into the range where, thanks to the proliferation of numerical algorithms and just sheer AI flops, we're able to do these things on smaller sort of university-sized resources. So all of this is sort of cool. And once we have this, we can try and use field theory to analyze what is happening to spectroscopy. This here is the excitation spectrum of one of the simplest materials we have. This is solid silicon. What you see here is, what we would typically call the band structure. And it doesn't really look too good. I mean, for a band structure, you would expect sharp lines. We know that silicon has an indirect band gap, which is one of the reasons why our solar cells based on silicon are very inefficient. That here is the indirect band gap, and that much is sort of visible. You can see that there's a hole in between where we have no excitations, but we can't really see that much over here. So if we really want to know about the excitation spectrum, that's just not good enough. And that was the status of this, circa 2020 or so, where we had all of this nice statistical mechanics, and we had all of these propagators, and the propagators could really be used to analyze spectroscopy in principle. But in practice, when we tried to do this, the types of results that we were getting were just not competitive with, what would come out of a simple density functional theory calculation that just gives you a band structure. So that was a big bummer. Mathematically, what we care about is a propagator. This is what we calculate. What we would want to have is a so-called spectral function. You can see that that propagator is related to this object, and this object is related to the spectral function. So in principle, all we need to do is take that integral here, discretize it in a kernel, invert the kernel, and we get the result right here. Unfortunately, you run into a typical numerical mathematics problem where the forward calculation here is not a problem at all, but the inversion of this kernel is very ill-conditioned, meaning that small uncertainties, even double precision uncertainty on one side, will give you huge uncertainties in your spectral function, and you have to regularize it with something like a smoothness criterion, which washed out all of these features. So along comes the pandemic, and with that, an extremely talented undergraduate student, Jenny Fay. She's now doing string theory at Stanford. And so with Jenny, we had a look at this, and we went to ask, can't we convince mathematics to give us better results for, that type of inversion problem? Let's look at what a Green's function or a propagator actually is. Let me write this in the complex plane. And you can see here that it is 1 over a partition function. Partition function is positive. It just enumerates the number of states that you have, times some matrix element squared, so that's also positive, times something else that is positive, divided by some energy denominator. And so what you can see is that if you take that z here and you put it anywhere in the upper half of the complex plane, then the imaginary part of that function is always negative. And it just so turns out that back in the 1920s, people were looking at measure theory, and they were looking at functions that they could analyze with complex analysis that were known on the boundary. And it was Mr. Neven-Linna here that basically said that, well, functions of that sort are, have funny mathematical properties that we can use for good. They're now called after him. These are so-called Neven-Linna functions. And it turns out that all the functions we work with in field theory are Neven-Linna functions. All the susceptibilities, all the Green's functions, all the propagators are variant of that funny functions. Now, Neven-Linna functions have a one-to-one correspondence to Schur functions. Schur functions are so-called contractive functions that map the open unit disk into the closed unit disk. Basically, every time you apply a Schur function, it shrinks you towards the center. And there's a good theory of continued fraction that we can use that really back in the 1920s people have explored to great detail. And if you go and look at 1918, Israel Schur über Potenzreihen, die im Inneren des Einheitskreises berechnet sind, you find out that, well, he actually gave you a numerical algorithm to compute those Neven-Linna functions. And in fact, if you give Mr. Schur from 1918 a bunch of propagators that you've computed on the contour, he can tell you not just an analytic continuation of what a spectral function should be like, he can give you a function space that defines all possible functions that have the right analytic properties and are consistent with your input. And so why do I bother you with mathematics from the 19-teens? Well, it turns out that Mr. Pick here, who was an Austrian mathematician at the time, said that, that function space is actually very small. If you just give me a bunch of points in a unit circle and you try to put one of Schur's functions through that, chances are it doesn't exist. In fact, only if you have this matrix here, which is called Pick matrix now, which is basically 1 minus value of the propagator at point I times value of the complex conjugate of the propagator at point j, divided by 1 minus frequency I, frequency j complex conjugate. You build that matrix, you diagonalize it, it ought to have positive eigenvalues only, and otherwise it is not a valid solution, it is not a valid field theory object. Well, it turns out, most of the matrices, if you randomly make them, you diagonalize them, you get about as many positive as negative eigenvalues. So this is a very, very restrictive criterion. And so mathematics itself tells us that the space of valid functions in field theory is actually really small. And when we're doing our continuation, we're allowing for all of these functions. We're having way, way, way too many. So rather than regularizing them with a smoothness criterion, we should just use the right type of function space. And with the same type of finite temperature field theory, we can now get very, very precise spectral functions that allow us to really do optics experiments simulated on the computer, going from, basically, well, you need new glasses, to, yes, this is a triple degenerate point. There's a double degeneracy, there's a sharp band, it disperses like this. Here's some symmetry breaks, and you have single, states over here and so on. This is, by the way, as you go around in reciprocal space of that particular system. And so with that, we have now established the formalism that allows us to not just compute quantum statistical mechanics, but to really look at response functions, in simulated computer experiments for realistic systems. Now, this is status, circa 2020, also circa 1920. Really nothing changed over a very long time over this. This is once we figured out how to use complex analysis. This here is the newest and best of that, which is now not an interpolation method, but it is actually an approximation method based on a radar methodology that makes connection to very interesting mathematics from signal processing and control theory. And so what I wanted to say with this is that even as a numerical physicist, if you use mathematics for good, and you're not too much afraid of complex analysis of the 1920s, you can take these methods and really supersize and supercharge your calculations. And so a lot of good numerics really consists of not just taking a problem and discretizing it and then throwing it on a large computer, but in developing algorithms that make use of the most advanced theoretical tools that we have, and then only then going the rest with high performance computing. All right, so over here we have Dominika, who's now also at the University of Warsaw, and works a lot on the real materials aspects of these things. And so really one of the things that she found out is that one can use these methods not just to do non-relativistic quantum mechanics, but there's a very simple modification to now also look at spin-orbit coupled materials. And of course, spin-orbit coupling becomes important whenever you go low in the periodic table, and almost all of the systems that we care about, are relativistic in some way in that they exhibit spin-orbit coupling. And with the newest types of technologies, we're now really able to use at parameter-free ab-initio spin-orbit coupled compounds in realistic systems. All right. Now, that is just weak coupling theory. And weak coupling theory works well for the upper part of the periodic table and for basically any sort of system where you don't have very localized electrons. It does not work well whenever your electrons start to become local. Of course, a lot of the interesting physics that I talked about, from plutonium to magnets to superconductor, has d electrons and f electrons, and all the d and f electrons are, of course, very well localized, and that's precisely the place where something beyond simple weak coupling theory of the 1960s is needed. And so it turns out that in that system, you can talk about doing a weak coupling solution for almost all of the system. You can then identify those parts of the system that are strongly correlated. And you can say, well, I need a non-perturbative solution for those parts. I don't need a non-perturbative solution for everything. I'd love to have a non-perturbative solution for everything. I can't afford it, right? But if I am to get results, let me at least take out some of these orbitals, for example, some of the d orbitals or some of the sp of the D and F hybridizations and so on, and let me put those into a special space where I solve those systems non-perturbatively while embedding them into a background of perturbative solutions. And I can make that mathematically exact with so-called phi and psi derivable theories, where some of the system is solved with just low order diagrams, and then some of the orbital subspaces contain diagrams to all order. And it turns out that the solution of the, I think I have that over here, right? That the solution of a system which is coupled between a correlated space and a weak coupling background consists to the solution of a so-called quantum impurity problem. A quantum impurity problem traditionally was simulating a strongly correlated atom that was an actual impurity like cobalt, adsorbed or embedded in a matrix of other materials, for example, cobalt on copper, which was the surface scanning tunneling experiment that I gave you. So these were actual impurities, or copper in gold was another one, sort of traditional example of an impurity that people wanted to understand. But the same type of mathematical construction also appears when we're looking at very strongly correlated orbitals embedded into a weakly coupled background that comes from other other sources, say S and P electrons, whereas we do the D electrons non-perturbatively. And so solving a system then like that means that we have a strong coupling, sort of exact solver for some of the system that has to be very small because the exact solution will be very expensive, embedded into an approximate but good enough solution of what's happening everywhere else. And so here I can give you a typical example. This is strontium manganate. Strontium manganate is an insulator. It is an antiferromagnetic insulator. And if we do weak coupling theory for this antiferromagnetic insulator, you see here the excitation energies in eVolt, and you see the blue curve here at the Fermi energy near zero. You see that there is some density of states near zero. That means that within weak coupling theory, strontium manganate is a metal. And so it is not just a quantitative fail of weak coupling theory, it is just qualitatively totally wrong. This material is not a metal. And so that means that the weak coupling theory of the 1960s is nice, but it's not good enough and we need something better. If we then say, well, this has manganese and manganese has strongly correlated d orbitals, and due to symmetries, those 5 d orbitals, they split into 3 plus 2, and let me identify the 3, those are the partially occupied. And let me just surmise that strong correlation happens on those 3 free orbitals. Well, if I do that, then you can see strontium manganate does become an insulator. And if I then say, well, maybe I was not quite right, it's not just the manganese T2G orbitals, but it may be also, in addition to that, the manganese EGs, which are the other 2 of the 5 orbitals, or maybe oxygen orbitals from the manganese oxide that are, from the strontium manganate that are there, or any of these other, I can add those 2 to a strongly correlated subspace. And I can't solve the entire system exactly, but I can gradually switch on some of these orbitals and I can check, does anything change between, beyond those, strontium manganates and manganese orbitals? And the answer turns out, yeah, very little changes. So that the sort of the big change happens once we allow strongly correlated electrons to be on the manganese T orbital and T2G orbitals, and all the rest is sort of, minor phenomena on top of that. And so that now, without any sort of adjustable parameter, allows us to converge towards the exact limit of these strongly correlated materials. Here's a different one. This is strontium vanadate. Strontium vanadate, thank you, is a good metal. If we solve strontium vanadate within weak coupling theory, we get a sort of, a little bit disappointing metal. It's fine. It's not very good. What's really characteristic is this sharp peak here, which is the so-called quasi-particle peak, which shows you that there are very strong correlations in that metallic state. And you can see that the moment we start adding additional correlated orbitals to this, like so-called T2G and EG orbitals, we're starting to see a quasi-particle peak here rising. And that really shows you that we can gradually ramp up the correlations of these materials to slowly converge to the exact limit, at least for small unit cell materials. So in this field, we have this idea or this dream of having some sort of convergent hierarchy, right? A knob in our theory. And we want to be able to turn that knob in that theory. And as we turn that knob, our calculations will get more and more expensive, but our results will get more and more accurate. And so if you don't like our result, give us more CPU power, we'll turn the knob a little bit, and we'll give you a smaller confidence interval. Each additional step, either that may be an additional step in a theory, that may be an additional, an additional set of diagrams, an additional set of orbitals, whatever it is, right? It will increase the complexity, but it will get you closer and closer to the exact result. And so if you look at much of numerical analysis, this here is, by the way, is a breakthrough simulation of an electromagnetic field here, That's standard practice in all of these other fields. If you've built a turbine in a fluid dynamics simulation, you start with a very, very coarse simulation of what's happening then. And then you see that, well, some of that fluid becomes turbulent in some part, and you go do a better job at just that part where that turbulence appears. Just the same over here. We do a sort of very generic, very bad job at a first initial solution with 1960s quantum statistical mechanics. And then we go in and we see, well, probably something's happening in those orbitals. Let me try and go up that hierarchy. Let me make that result better and better and better and see how much of it changes and whether we can converge. And that really helps you to go from cheap but fast to expensive but accurate, and allows you to gradually then ramp up the precision. And in the field, by the way, this is called the so-called Jacob's ladder, where as you go up and up, rung after rung, you come, sort of closer and closer to your nirvana. Anyway, our hierarchies are manifold. We don't just have one. We have system size that we need to converge, diagram types, the entanglement, the diagram order, the basis set, the case-based discretization, the embedding subspace, and so on. And it's a work in progress to really find out for which systems and how we need to converge which one of those and what is the leading uncertainty that we find in those systems. And so where do we stand? First of all, we have a solid foundation to perform many-body theory ab initio without adjustable parameters reproducibly and accurately. What we specify is the electronic structure, basically where our nuclei are, what our basis set is, and what our approximation is. And from then on, if you do the calculation, you better get the same result as we do. The leading error is the weak coupling approximation. All the other approximation, like finite size, basis set, starting point dependence, and so on, they're either eliminated or they're under control. We can actually do relativity. We can definitely do excitations, right? All of these band structure, all of these, photo emission response functions are about excitations. We can see that increasing the diagram order is not always a good way forward. I didn't show you results for that, but embedding seems to be the right way to go. We have very close connection to the experiment at our fingertip, right? The propagators that we're working with, the response functions, the susceptibilities, those are exactly the objects that experimentalists are probing. And I would say we still have a very long way to go to routine parameter-free ab initio calculations the same way that DFT is doing it. But we have here the hope for getting strongly correlated systems done nicely, right, and in a controllable way. And so with that, I would like to thank my collaborators, Gianni for doing the original work in analytic continuation, Lei also doing analytic continuation, Yang and Qianan were doing a lot of the real materials calculation, Andre was doing the radar work that I showed you, the newest version of sort of the spectroscopy, and a lot of it is done in collaboration also with Dominika, who's now at the University of Warsaw. And with that, thank you very much for your attention.
Thank you, Emmanuel, for a very nice and engaging talk. We have now questions for time for questions. Please, Wojtek.
Yes, hello. Thank you very much for this talk. I could really see the effort put into make it accessible for broader audience as we have in this institute. So actually, I'm a physical cosmologist, but I found many points of your talk very corresponding because I also use supercomputers to study large-scale structure of the universe, different emergent phenomena whatsoever. But I was puzzled by one thing, and I would like to hear you comment on point on this. It seems to me, maybe I got it wrong, that you use words precision and accuracy interchangeably, although here in astronomy and cosmology, we have very big problem with them. We know we can get always more precise, but doesn't necessarily mean we get more accurate because we actually, have some hidden systematics or missing some piece of physics. So do you have any kind of a problem with that? And where would you put, okay, you told me that if we give you a bigger computer, we can make your calculations more refined, you get more precise, but where is the accuracy here? Can you put error bars or something like that from experiment or some kind of a callback to the data?
Right. So that's a very good question. And I want to discard experiment as a comparison point right at the start. The reason for that is we know the theory that we should be simulating. And I brought it up at the very beginning, right? And we know the theory works. So, right, that's our homework, right? If we're not doing this, we're doing it wrong, and hopefully the errors that we're making are small. Now, it is on us to show you that the errors that we're making are small in every step. Precision versus accuracy, the way I see it is we make mistakes along that way every single part of the way. And some of these mistakes we're very good at quantifying, double precision errors, things like that. Others were really not. Others were good at quantifying in principle, but not in practice. And getting to, because the calculation has to be both practical and, accurate enough. A good colleague in the field who's doing density functional theory says, if the calculation doesn't run in 4 hours on a laptop, it's not worth it. We're using half a year on supercomputers for these things. So there's this trade-off, right? But there's a question of what is the right knob that will make you more precise. There's also the risk that you have your favorite experimentalist who gets result A, and you start tuning until you too get result A, right? And that's sort of what we want to avoid, that, very many of these materials theories have free parameters in them that you can use to adjust that. And that's a big danger. And sort of we deliberately take a step back here and say that this is not the business we're in. Even though if you're in an engineering department, this may be the business you have to be in, right? Now, quantifying those different problems and whether you're talking about numerics or theory is difficult, and it is material dependent and situation dependent. And we can go and pick one of those, and I can make you a hierarchy of where I think that the most likely approximations are, and then we can discuss whether we can do anything about them.
Okay, next question.
Thank you very much for your super interesting talk. I have actually a couple of questions, or maybe 2 questions and 1 short comment. First question is, I come from strong interaction physics, and so the notion of effective theory is very close to me. And back 30 years or 40 years ago, when people thought about effective pion-pion interaction theory, it was just an expansion in terms of the ratio of pion momentum to its mass. And the whole problem was to calculate coefficients of these operators, and they were not calculated. It was too difficult. They were just fixed by experiment. Now, you seem to be able to compute behavior of a very complicated system, excitation energies, without really thinking about some hierarchy of scales or expansion in some physics parameters, so to speak, right? Expansion in some physics. Would you see a space? On the other hand, you have just demonstrated that you treat some part more non-perturbatively than other, right? So it is a similar. Would you see a sense in developing some sort of expansion, effective Hamiltonians, and just telling the world what the coefficients are, how they are predicted by your theory? Mm-hmm. And in this way, although it not necessarily will increase accuracy, it might increase, in a certain sense, an insight, how the theory really works, how the scales match. I understand very well that you have, in such a complicated system, tens, if not hundreds of scales, right? So that's very non-trivial. Right. That's my first question.
Okay, so let me ask that question. Actually, let me give you an answer for that question for strontium manganate. What you call the low energy model, that procedure of generating that model and fitting it to something that has a name in this field is called downfolding. Downfolding means basically taking the entire system and then condensing out a few parameters in a low energy subspace that one needs to consider in order to get good result. Here strontium manganate is a good system where, I could say that it is really the strongly correlated d orbitals that we would have to consider here. And so let me construct a model for just those orbitals, and let me toss out the rest. If I do that, I will get an answer for the d orbitals. The d orbitals will become insulating. You see them right here. The green one, the blue ones. But you can see over here that the green ones, which are the oxygen orbitals, which are in the weakly coupled space, already make the system here metallic. So if I spend all of the effort to do a good job at the d orbitals, the strongly correlated part, I'm still going to get the wrong result because the strongly correlated part, the low energy degrees of freedom, influence the other degrees of freedom again and readjust them. Which means that the naive construction of saying, oh yeah, I'm a chemist, I know that d orbitals are important in this thing, let me take those and calculate it, that's too naive, that doesn't work. Now there's a big field of actually doing this right. And I'm not saying that this is the wrong approach, I'm just saying that it's not the approach I've been following here, and it's often very successful. And as you say, one of the things you get from that is insight. For example, if you're looking at magnetic response functions and trying to explain neutron scattering signals on compounds like this, almost always what you're doing is fitting a couple of simple Heisenberg constants to what you're finding, right? And those are really fitted to experiment. You get the neutron dispersion, you look at it, you fit it to a magnetic model, and then you look at what the temperature evolution of that model is doing. You're not going the sort of, big iron electronic structure route for this, mainly because it's very difficult to do that. On the other hand, if you could do that, you would get an unbiased result, a simulated neutron response signal, which you could put to the actual one and then say, hey, look, guys, we're not finding the same. Something went wrong here somewhere. Let's understand what it is. Or, yes, we actually understand that material to the precision we care about. So that downfall dimension is actually interesting, and it's really non-trivial.
Okay. One, a bit quicker. Yeah.
Okay, just this comment. It just happens that I teach in elementary school physics, and you mentioned on your first slide that we all see the Newton's laws around, and I can tell you that basically the first Newton law is a very difficult threshold. The inertia, the concept of inertia and consequences is extremely difficult threshold. They all think Aristotelian way, and because of that, I would love if you allow me to be able to show on Monday your first and third slide to my students, if you don't mind.
Of course.
Okay, okay, we have still some time for one or two quick questions. Okay, Nikolai.
Okay, so your talk is very far from my field of research, but there was one topic that I felt that it rings a bell, and it was the idea of embedding a system you can solve exactly into a larger one which you cannot solve exactly. In relativity, you sometimes take a small object and embed it into a larger gravitational field using something called matched asymptotic expansion theory. Do you use anything like that as well? Or you, for example, make use of the ratio of scales of the big system with the small system or things like that?
Not precisely like that, because the scales are basically not different enough. It's a mess, and you got to be able to deal with the mess. There are good mathematical concepts that help you here, but they're a little bit different. Basically, the way that we think about it is that you have a consistent and conserving theory of statistical mechanics here, and then you go about it with scissors and you cut out the stuff that you think is not relevant. And whatever you're left with, you need to solve. Some of this you can solve by explicitly summing up the diagrams. Some of this need a non-perturbative construction. Some of this you've then counted twice, so you need to subtract it, which is not a problem because you know what you've counted twice, right? And so in this way, we basically make a patchwork of different parts of our space that we need to consider. But there's no nice separation of scale or renormalization or so that you could apply here and still be quantitative.
Okay, one last question by Professor Zążewski.
Yes, it's a question which bothers me for a long time. You've mentioned a powerful method of density functional. There are many cases for which the system itself, described in terms of the Hamiltonian, has some obvious symmetry, for instance, spherical symmetry, while some solutions of the density functional method break this symmetry. How come?
Oh, I think this has a. Let me take a step back and take H2, right, hydrogen, and let's, two hydrogen, you get one, I get one, and we walk away, right? What we would expect is that I end up with one electron, you end up with one electron, right? If we walk far enough. What you get in many of the theories